at the Institute. We're a collaborative research institute for theoretical computer science, supported in large part by the Simons Foundation. And we run 2 programs each semester. I've been doing that since 2013, and each one attracting something like 60 or 70 long-term visitors, usually to Berkeley, and they include a boot camp like this one and 3 workshops, which also involve a lot more people. So this semester, we're very happy to be running 2 programs, the Theoretical Foundations of Computer Systems and Satisfiability, Theory, Practice, and Beyond. And together those involve around 120 long-term participants, including 13 research fellows. So welcome to the boot camp for the Theoretical Foundations of Computer Systems program. Of course, we're really disappointed we can't welcome you in person to Berkeley. We've got a pilot program for outdoor in-person collaboration starting soon as part of this semester's programs, but we can't run events like this one in person right now. Let me say a few words about the goals of these boot camps. They're intended to be a kind of social and scientific icebreaker for the programs, to get people talking to each other, to also get them on the same page technically, across the spectrum of program themes. And I guess they have a pretty significant archival value as well. A nice snapshot of the state of the art in a field. The talks are all archived on our YouTube channel and website. Okay, let me introduce Ashley Hassan, our events coordinator. Ashley's been dealing with the schedule and logistics for the bootcamp here at the Simons Institute. She's here somewhere on Zoom. So thanks to Ashley for that, and you'll see her in Gathertown during the week. Also, a thank you to the organizers of the bootcamp, to Moshe Vardi, to Pavel Cherny, Thomas Kolkumbe, Marta Kwiatkowski, Ruzika Piska. So a big thank you for putting together a fantastic program and a great set of speakers. Okay, so let me hand over to Moshe to say a few words about the bootcamp.
Thank you, Peter. So I think you all know about the division of theoretical computer science into the volume A, algorithm and complexity, and volume B, more logic and algorithms. And we have been putting a lot of effort to DOS tend to be more volume A. Volume B is a bit more international. And the Simons Institute received 2 proposals, one on the theoretical foundation of computer system and the other one satisfiability, and both were selected. But the universe seems to be unfriendly towards volume B and decided to throw a monkey wrench there. So we have been now kind of scrambling to deal with the pandemic. And in particular, because volume B is more international, it was more of a challenge to try to figure out how do we virtualize ourselves, because we have people here all the way from the West Coast who are grumbling about having to get up so early, and people in Europe who have to put the kids to bed. And beyond Europe, we just could not find any other way to do that, or the other ways to do everything twice. It just become unmanageable. So we end up converging on 2 hours per day, and we have what I call seminarize all the workshops. So all the workshops are now horizontal rather than vertical, so to speak. And it's a grand experiment, and we will have to see how it works, but it might be the future of conferences. So let's all work together. I mean, the organizers don't have some magic answers. We kind of rely on all of us working collaboratively to try to make the best of it. And with that, I'm happy to introduce our first speaker, Mikolaj Bojańczyk from Warsaw, who is going to give us the bootcamp on logic, which will be complementary to the, in particular, Mikolaj lecture and Orna Kupferman lectures are going to be quite complementary, really kind of 2 pieces of Lego fitting together. So I encourage you to, at the minimum, to try to attend both, because I think you'll see the same elephant from 2 different perspectives. Mikolaj.
Thank you, Moshe. Since I have small kids, I get to know a lot about Legos, and I'm afraid that I hope that they will not be like cheap Legos, which don't really fit together, but tend to fit together. So thanks a lot for this introduction. I'm rather stressed to open what Moshe called the future of conferences. And my stress is also increased by my rather presumptuous title, which is logic. So logic is, of course, a huge field. And I'm not competent to speak about it. Well, Moshe probably would be in full generality. So I will give a very biased talk. And now we're all familiar with biased communication. So there will be some things that I will should say, but I will not say at all. And there will be some things that I will say twice. So that's going to be my bias. And the bias is towards automata, which is the central topic of Orna's talk tomorrow. Now, since these slides are available online with sound, well, a superset of these slides, I think the value of this particular meeting is that you can interrupt me all the time. So I think it's not important if I reach the end of my slides, as long as if at any moment you want to say something, you want to criticize something, you want to say that you think about it differently, please go ahead and do so. This is what, I mean, it's supposed to be interactive, okay? So don't worry if we don't reach the end of the slides. So I'll begin by saying what I will not talk about. So as I say, it would be rather presumptuous for me to say that I'm talking about logic in general. So logic is huge. And I will be mainly talking about, are my slides visible?
Not yet.
Oh, okay, that was a big...
no, we need, who is the host of the meeting? Ashley, are you the host?
Maybe I think I didn't press a button.
Okay, okay, good.
Are they visible now?
They're visible now, yes.
Yeah.
It's not going to be in general about logic in computer science, but it will revolve around first order logic and its variants and, well, you know, which formulas are true in which models. So I'll try to give you a brief overview of some mainly very old results about how can you have algorithms that check properties of formulas. And my bias will be about algorithms which use automata. Okay, and so there's lots of aspects of logic that I will not talk about. So maybe I guess if you're in the US, then probably logic means Boolean formulas under satisfiability. And I guess if you're in the SAT program, that's also an indication that you might think about this. So I will not talk about that. It's a huge topic, not discussed. I will not talk about other aspects of logic, such as, I don't know, intuitionistic logic, which due to its connection with lambda calculus is also an important topic in theoretical computer science. This is something that I will not talk about. I will not talk about proof assistance, again, a big topic now, and this is also logic. I just list a number of things that came to my head, free associations with the word logic, which I'm not going to talk about. I'm not going to talk about proof theory, and I'm not going to talk about, say, temporal logic, something that will probably play a role in Orna's tutorial tomorrow. Okay. What I will talk about is, this problem, which is the satisfiability problem of deciding if a formula phi is true in some model. Typically, it's going to be a formula of, say, first order logic or some variance. And then the question is going to be what to do about the fact that this is an undecidable problem. And in my talk, it's going to be what to do about this fact in a way that involves the word automaton. Okay. Another problem that I will also discuss is the model checking problem. So deciding if a formula, where we have the model, we have the formula, and we want to know if the formula is true. And then this model checking problem can be discussed from several different perspectives. I think that Moshe would call them data complexity, query complexity, and combined complexity, which would be, one variant is that we fix the model, and then the formula is the input, and then you have the other combinations. Okay, so my talk will be structured around these three problems. And I will begin with this one, which I think is maybe the most classical problem, like 100 years old in logic. So, which is, we fix some important structures that we care about. I don't know, the real numbers, for example, with the field operations. And we want to know which formulas are true there. And then I will also discuss the satisfiability problem with, as I say, an emphasis on automata methods. And finally, I will discuss the model checking problem where we fix a formula and then the structure is given on input. So typically it's going to be a finite structure that I will care about. Okay. So let me I want to say that there are slides for each of these parts, and they're more in depth. But here I just want to go over some subset of these results. So let's begin with the problem where we have fixed a structure, and then we want to we're given on input a formula of first order logic, and we want to know if it's true, and via an algorithm. So just in case you don't remember, first order logic is the logic where it's not propositional logic. It's where you have a structure which has elements and you get to quantify over them. And the structure has extra, structure, relations, and you get to write about that in your formula. So here's a formula which tells you, I guess, that the binary relation R is a function, okay? So the problem that I will discuss in this first part is you have a structure M and you want to know when is it, let's just say, decidable. And if decidable, then what is the computational complexity of the problem? We are given on input a formula, a sentence, a formula without any free variables, and want to know if it's true in our structure. So let me begin from the low side. So maybe the simplest possible structure you can imagine has just two elements. And it has only one relation, which is equality. Well, actually, I will always assume that equality is for free. This is not an obvious assumption, but this is one I will make. And so I could just say there's no relations, but I feel uncomfortable not indicating a list of relations, so I just write equality. And then already for this simplest structure, the problem of given a formula, whether or not it's true there, is p-space complete. And it's easy to encode quantified Boolean formulas where 1 is true and 0 is false, or actually the opposite way, because you have, with equality only, you don't know which one is true or which one is false.
Mikolaj, the very, very left of the slide is chopped when I look at it.
Is that true for other people?
It's true for me.
Yes.
Okay, is there a way you can slide? It's like one character is missing. If you can shift it right a little bit.
Yeah, okay, then I have to exit full screen.
Okay, now we see the whole thing. Before that, we saw first order logic.
Well, that way I could claim a new logic.
Yes.
Is it now? Is the logic,
yes.
has it returned to its classical form?
Yes, yes.
Well, that's the only thing we needed, one more logic.
Yes.
Okay, so if you fix a structure which is finite, such as the simplest possible structure is going to be p-space hard, and it's also going to be p-space because the naive algorithm where you just every quantifier you replace it by a for loop, it's going to run in polynomial space, and because every element can be represented in logarithmic space. Okay? So there's not much interesting to say about the decidability or complexity about the model checking problem if we fix a finite structure and we vary the formula. So the interesting cases are when we have an infinite structure. And then it's not clear if it should be decidable. And actually, this is going to be maybe the focus of this part of the talk. So decidable or not. So I guess a super classical one would be a structure that's called, I think, arithmetic without any adjectives. And here we have say the natural numbers or the integers, it doesn't matter, with the field operations. And if you are given a formula of first order logic and you want to know if it's true in this particular structure, this is an undecidable problem. And this is, well, it's roughly Gödel's proof. Because you can encode a list of numbers using a single number, and using a list of numbers, you can encode a computation of a Turing machine. So once you are comfortable with these types of encodings, then you can just write in a formula which says that this such and such Turing machine holds. So it's an undecidable problem. And this motivates the search for, for what structures can you make it decidable? And a famous result, which is due to Tarski, and I think it was proved, he proved it before the war, but the published results are in Berkeley, were published when he came to Berkeley after the war. It says that if you consider the field of real numbers, then the problem, given a sentence, whether or not it's true, it is a decidable problem. And this already is connected with a method, which is the quantifier elimination method. So what Tarski showed is that this theory is decidable because it has quantifier elimination in the following sense. So for every formula which may have 3 variables, it is actually equivalent to a finite Boolean combination of polynomial inequalities. So here a polynomial, it has integer coefficients and it uses the variables from the formula. So for example, consider a formula which has 3 variables, a, b, c, which are free, and it says that the quadratic polynomial ax squared plus bx squared plus c has, the quadratic polynomial with coefficients a, b, c has at least 1 root. So according to Tarski's result, this is described by a quantifier-free formula, polynomial combination of polynomial inequalities in the 3 variables. And actually, if you figure it out, it's something that I guess kids learn in school, which says that in Poland, at least it's called the delta. So we say that b squared minus 4ac is greater or equal to 0. So Tarski's theorem is aware of this result and other results. I think it's a funny story because if you look at Tarski's original proof, it is, well, if you like look at the heart of it, it's just taking a school algorithm for describing the shape of a polynomial with 1 variable. And Tarski, when he was in Poland, he was teaching high school mathematics in a girl high school. So a story that I made up is that when he was teaching this high school mathematics, he got bored because he just keep on proving, analyzing the shape of this polynomial with 1 free variable, and always using the same tools. And so, like a lesser person, such as myself, would go, "Oh, I'm such a great scientist. Why do I have to teach about polynomials? I should be doing more important things." And Tarski was not such a person. So he decided, "Oh, okay, I'm teaching this stuff, which I find boring, but why is it boring? And in what way is it boring?" And then he formalized that it is boring in the sense that there is a decision procedure which does this. I talked to some historians of mathematical teaching, and I think there's evidence that my story doesn't add up, but it's a story. Okay, si non è vero. So another example of a story, well, there's no story here, is Pressburger arithmetic. So Tarski arithmetic is kind of strange because you'd think that there's more real numbers than natural numbers, so they should be harder, but they're easier. So somehow it's hard if you're dealing with natural numbers as opposed to real numbers. And Pressburger considered the case, okay, we use the hard natural numbers, but we don't have multiplication, we have addition only. And then he proved that this theory is decidable. So if you're given a first order formula, well, you can't say much. You can say maybe something like there's infinitely many even numbers, because you can say there's for every x there exists a bigger y such that y is equal to z plus z for some z. That's a thing you can say in Pressburger arithmetic, maybe not super exciting as a mathematical theorem. And then Pressburger, well, this is modern terminology. He showed that every such formula has a normal form, which is, well, now it's called semi-linear sets. And you can effectively transform every formula into a semi-linear set and work with these in a computable way. And actually, Pressburger arithmetic, I mean, I'm sure many of you know this, it's a fundamental logic in verification, because you can, many things are decidable because you can express, well, at least a simple argument for decidability is that you can express them just using this logic. There's also a similar thing to Pressburger arithmetic, which is called Skolem arithmetic, where you get to multiply, but you don't get to add, and it is also decidable. Okay, So those are some of my examples of structures which have a decidable first-order theory. Then you can go to higher logic. So one logic, and this is actually the direction that I'm interested in this talk mainly. So you could say, well, why not just, why do I quantify just over elements? Why not quantify over sets, or maybe over, say, relations? So relations of RT2, a set is a relation of RT1, and so on. And this one is also kind of trivial from this perspective, because if you take any finite structure, then second order logic is going to be p-space complete for it. So the lower bound is inherited from first order logic. Now here you don't even need to assume that there's two elements. And the upper bound is just, again, the trivial algorithm. And it is undecidable for every infinite structure, because if you get an infinite structure, and then you can guess addition and multiplication using second order logic and be done with it. So there's not much to say for second order logic. But this leads me to the logic, which is the one that I care about most of all in my talk, which is, well, if you haven't seen it, I cannot imagine that somebody has not seen it, but if you are such a person, then it might be surprising, but it turns out to be extremely important in this field, which is monadic second order logic. So this is like second order logic, but it is restricted. So when you get to quantify over elements, but you only get to, when you want to talk about objects of higher order, such as binary relations and so on, you only get to do unary relations.
Mikolaj, quick interrupt?
No, I said no interruptions.
No, you invited interruption.
Go ahead, Moshe, sorry.
Fixed structure here, right?
Yes. Did I make a mistake somewhere?
Then why is it p-space?
Well, you can, did I make a mistake here? So you mean the upper bound, yeah?
Yeah, I mean, because now to represent a relation, it's of exponential size, right?
Correct.
Even of it.
Yeah, correct. That's it.
Yeah, but it's a fixed finite structure, so it's constant size.
I know, it's constant size, but the relations are the structure is fixed.
If the arity of the relation is part of the input, then in fact, Moshe is right. I made a mistake.
The relation is of exponential size, yeah. So this is some kind of this is some weird complexity class in the.
Yeah. I'm sorry. Yes. So it's it's between exponential and p-space.
Yeah.
So it's you're right. There is I guess a class for that. Yes. So thanks. In my hurry to disregard second order logic, I run over a pedestrian. I apologize. Anyway, what I want to talk about is this MSO. Okay. So it turns out that this logic it can be quite well understood, and this will be the main theme of my talk here. So let's begin with. So this is I think it's a question that, as far as I know, goes back to Tarski. It's I think there's from his lectures in the 50s in Berkeley, which is what if I take the ordered natural numbers, and then I ask which monadic second order logic formulas are true there. So I fix this structure of the ordered natural numbers, and I'm given on input a formula, an MSO formula, and I want to know if it's true. So, for example, if you don't have the order, then it's kind of easy to see that the problem is decidable, because roughly speaking, you can first, MSO doesn't contribute anything. You can eliminate set quantifiers. The only thing you can say is that this set has at least 10 elements, and this element belongs to that set. So this is, it's I think, a rather easy argument. But if you have order, then the things become quite interesting. And by surveying like the first result, which was proved on this topic, which is that a variant of this problem is indeed decidable. The problem itself is also decidable, that will be later, but the variant will be somehow most connected to what I will talk about later in my talk. So weak MSO the syntax is the same as MSO. So you have quantifiers which say for every element X or exists an element X, and you have quantifiers which says exists a set X and for every set X. However, well, it's a different X, a capital X because it's a set. However, the semantics are different. So when you quantify over a set, it's meant to be a finite set. So for example, if you write the formula on the left, well, it's the same formula, but you understand it in two different ways. If it says there is a set which contains all elements, then this is true if you allow infinite sets, but it's false if you only allow finite sets. So in principle, these logics are different. So they're incomparable somehow. But for the natural numbers with order, they're comparable because you can express in the full MSO, non-weak logic, that a set is finite by saying there is a finite upper bound on its elements. And therefore, every formula of weak MSO can be converted into an equivalent formula of non-weak MSO. But as it so happens, the converse is also true, but that's a non-trivial result. Okay. So this is a theorem, and you will find a maybe slightly unusual list of authors here of length 5. And I'll explain this unusuality in a moment, which is that this is the late 1950s, which says that the weak, this weak theory, so the question of given a formula of weak MSO, whether or not it's true in the natural numbers, this is a decidable problem. So why is that? Well, the idea is, it's a frequent idea. If you want to prove a theorem about a logic which has quantifiers, you typically want to prove something about subformulas. And therefore, if you want to do an induction over formula size, for example, and therefore you need to treat formulas which have some free variables. So consider a formula which has free variables, in this case, 3. So it has a first order variable X, which is meant to refer to an element, a natural number, and 2 second order variables, Y and Z, which are meant to refer to finite sets of natural numbers. Now, this formula has a semantics. So it describes as a set of triples of the form a value for X, a value for Y, a value for Z. X is going to be a number, Y and Z are going to be finite sets of numbers. And you might want to wonder how you can represent this in a finite way. So, for example, in Tarski arithmetic, we would say you can represent this using a Boolean combination of polynomial inequalities. In Pressburger's theorem, we would say you can represent this using a semilinear set, whatever that means. And that's not going to work here. And what is going to work, and this is an incredibly influential idea, is that we're going to use an automaton to represent this set. So how do you do it? Well, imagine that you have, say, a possible values of the variables. So you have a number X and 2 sets Y and Z. And since the sets are finite, you can just write them as a word, where the ith letter tells you about with the number I, which sets does it belong to. So you write, well, since Y and Z are sets, you can get plus or minus in some configuration of pluses and minuses. And since lowercase x is just a number, you get exactly 1 plus. Because there's exactly 1 number which is equal to it. And since these sets are meant to be finite, because we're talking about weak MSO, then at some point it's just minuses everywhere. So you can cut off the word, and you can this way you can represent your variable valuation as a finite word over an 8-letter alphabet in this case, which tells you the columns of the picture. So this way you can represent the values of the variables as a finite word, and you can use automata. So the lemma that you prove is that for every formula, some of the free variables are elements, some of them are sets, and then you say that there is, and actually in fact can be computed, a finite automaton that tells you if a representation of the variables is correct or not. So how do you do this? And it's a very simple idea. So you just do an induction on formula size. And if you think about the atomic formulas, which says this variable belongs to that set, that's something you can say in weak MSO, or this variable is smaller than that one, the corresponding languages are easily seen to be done by finite automata, which I think have 2 or 3 states in each case. Okay. And then if you, how else can you construct formulas? You can take Boolean combinations. Everybody knows that languages recognized by finite automata are closed under Boolean combinations. That's going to work out. And then you have to treat a quantifier. And this is an idea which maybe, if you haven't seen it, it's worth to explain with a picture, which is that quantifiers of logic correspond to projection. So what does that mean? So imagine I have a formula with some here some free variables, maybe all of them are elements, it doesn't matter, or they could be sets. So there's a corresponding language, and a word, okay, they should have been sets because there's lots of pluses. A word which describes them looks like this. So now if you create a quantifier, then the words which satisfy the quantified formula are obtained by taking a word which satisfies the unquantified formula and just removing one row, the last row in this case, the one that corresponds to the quantified variable. And so that means that the corresponding logical operation is just projection. It means it's an operation which takes words and for each letter removes some information in this case the last bit. And if you think now about regular languages, they're easily seen to be closed under projection, because one way to see it, for example, is if you take a regular expression and then you just for the language before quantification, and then for each letter you just write the corresponding letter with the last bit removed, and you get a regular expression for the projected. Okay. So that shows that automata have all of the properties which you would require of logic, and therefore they can be used as a normal form for logic. And if you care about complexity, then it's not going to be so good, because if you want to do Boolean operations, especially complementation, you would typically be interested in having a deterministic automaton, because complementation doesn't work well with a non-deterministic automata. And if you're going to be dealing with projection, the opposite is true. You are going to be typically interested in non-deterministic automata. And if your formula switches between quantification and existential quantification and complementation n times, then you're going to find yourself determinizing an automaton n times. And then making it not deterministic, and so you will have n times. You will have an exponential, and this is actually optimal. So it is of non-elementary complexity, this translation. So it's more n-fold exponential in the sense of computational complexity, where n is the number of alternations. So it's not so good in terms of complexity, but it's a decidable problem. Okay. So this is the automata method, and it turns out to be incredibly flexible, and I will give you some very important generalizations of it later on, but I would not discuss them in detail in this particular talk. So maybe you might want to ask, what is my letters? One of them is T for Trachtenbrot. So Trachtenbrot wrote a paper in 1957, submitted it in 1957, about synthèse logicznych sieci, I guess, and I'm not sure how my pronunciation is good, about the synthesis of logical nets, which are described by a one-place predicate, so by monadic secondary logic, and he proved the theorem there. So this is a paper which was published in Dokłady, in the Proceedings of the Soviet Academy of Sciences in 1958. That is one source. It's 3 pages long or 4 pages long. And to be honest, I'm not sure if the proof checks out, but you know, I'm not a fluent Russian speaker, so there could be. And it's nice because one of the technical definitions is a Sputnik. So this is a clearly sign of the times. So every formula has its Sputnik. That's one source, and the other famous source is a paper. Well, this is a conference version of Büchi and Elgot, and then the journal papers are separated in the same year. And so the conference version is short enough that I can put it here in full. So here it is, and that's the entire conference paper. I think you've got to infer some of the information from the kinds of capital or lowercase letters that they use, but it's an abstract. And the theorem says here, and you can see that the main theorem is not the decidability of the logic, but it is the automata method that is highlighted as the main result of the paper. However, if you open this, you see the next line. It's kind of funny because whenever you open an old paper, you find something strange in it, which says that actually the theorem about logic itself was known before. And this is Ehrenfeucht and Vott, and this is the E and V in my list of authors. And there's a very nice paper by Wolfgang Thomas, which appeared in the Siglog newsletter, I think 2 years ago, which explains the story behind that. So the original proof actually of these results was Ehrenfeucht and Vott. And the idea there is to encode finite words using ordinals. Like omega square and omega to the third and so on. And then there is a result that ordinal arithmetic is decidable, and you can reduce it to that. So this is our story. Maybe one more thing that's nice in this abstract is that a corollary of already pointed out by Büchi and Elgot in their paper, a corollary is that Pressburger arithmetic is decidable, and it's maybe nice to explain how, because it's very simple and yet also I think quite an important idea. So what is that? So what I want to show is, using this weak MSO theory, I want to conclude that Pressburger arithmetic, so the natural numbers with addition but not with multiplication, is a decidable theory. So you can represent that. And how is that done? Well, the idea is the obvious one. You take a natural number and you represent it using a set, a finite set, which describes its binary expansion. So you just do the binary expansion, and the digits in that binary expansion is your finite set. Is this clear? Okay. And now, well, you have to say that addition can be defined. So what you show, but this is school stuff, is that you can write an MSO formula for x plus y equals z. Because you just have to say how you do addition, you know, of three numbers. There's like a bit for carry or something, and you can all formalize this by using set quantification. And thanks to that, we know that if I take any formula of Pressburger arithmetic, which has some free variables, each one representing a number, then the corresponding NRE relation on binary expansions is definable in a weak MSO, and therefore also by an automaton, and can be which can be computed effectively. But actually, this method allows you to decide more than Pressburger arithmetic. You can add some other stuff that you could do with an automaton, but you cannot do with Pressburger automaton, such as saying that a number is a power of 2. Because if you have a binary expansion, then it's easy to see if it's a power of 2. It's just, well, it just has one digit, one non-zero digit. And then you can actually find out some kind of rather artificial, I would say, predicate, which you can also do. And then once you have that, actually, then it starts to become equivalent to automata. So if you extend Pressburger arithmetic with these things, then you get exactly the same thing as automata. And this result, if I say, well, I said Pressburger arithmetic is natural numbers, but if it's integers, nothing changes. And this is an example of this phenomenon here is something that's called an automaton group. So unfortunately, the word automaton group can be understood in 3 different ways, which is a little bit confusing. So one of them, the one that I'm using here, is actually the one that is never used, which is that you can represent the elements of the group by words, and the 3 place of the group operation is there's an automaton for that. That is not a way that anybody uses it, but there are 2 other understandings. One of them is that an automaton group, and this is the main one, you can represent the elements by words, and then it's supposed to be finitely generated, and for every generator, the operation of multiplying by that generator is implementable by an automaton. And that is something that is popular in group theory. I think that this was originally proposed by the famous geometer William Thurston, and then it's a thing. And then you can generalize this notion to, well, structures which are representable by automata and not necessarily, that are not necessarily groups, which was done by Nerodi and Husseinov. And then just to complete the confusion, there is a third understanding of automaton groups, which I think and I think these are not automatic groups, but they are automaton groups. And this is a completely different notion, again, popular in group theory, some kind of popularity, where an automaton group is as follows, you take a word-to-word transformation, which is definable by an automaton, a transducer. And then if your transducer happens to be reversible, then there's a natural group structure to it where you can invert it. So you take several such transducers and then the group of string-to-string transformations generated by them. And groups of this shape are called automaton groups, I believe. And then they are, I think, the world-leading counterexamples to some group theoretic conjectures, such as the Burnside question. So that's, but that's just a little digression about groups. So let's continue with our main theme. So these people, well, Büchi, Elgot, and Trachtenbrot, they proved that logic is equivalent to automata. In this case, logic being weak MSO. And then this was continued and by Büchi himself to prove the original problem, decidable. And then it was also continued famously by Rabin, for a generalization where you have, instead of the natural numbers, which is a linear order, you have all strings ordered by prefix relation, which is like a branching order, a tree order. And both of these theories are decidable, and in both cases it is because of automata. Now, in my extended slides, I discussed just a little bit about what these automata are about, but not so much. But the general idea of the proof is the same. You define a notion of automaton, which is expressive enough but it has to work over infinite objects now, to be closed under Boolean combinations and projection. And then the difficulty is, in both cases, the main difficulty is showing that non-deterministic automata are closed under complementation. And you can do it without going through deterministic automata, and then it's different. Well, there's stuff to say about that, but I think Orna will mention at least some things about that. And then maybe just to mention one like end of the line result, there's if you take the real numbers with order, then in fact the MSO theory is undecidable. So this is an ordered structure, but the automata don't seem to work there. And I think I have nothing to say in like one line about this result, except that it's proved using, you have to be crazy to prove it. If you look at it, he manages to encode in the end arithmetic, like natural numbers and addition. But it is, well, it's just crazy. I mean, the way you represent a natural number as a set of real numbers is just, but it's an interesting story, but maybe for another time. Okay, so that's a brief overview of a theory of structures which have a decidable MSO theory. And that concludes my part, where I fix the structure, and then I ask about the formula, and then the examples that I cared about mainly were where the structure is infinite, so it's not obvious if the problem is going to be decidable, and then the answer was, by finding suitable kinds of automata. So let me go now to the second part, which is where I am just given the formula, and I want to know if it's true in some model. Okay. And then this will be studied in several different variants. Well, there will be which logic do I care about, and which what do I mean by model. So if you take the most natural formulation, where the logic is first order logic, and then the class of models is, say, all models, then this is just Hilbert's Entscheidungsproblem. This is I think Hilbert stated it as not satisfiability, but validity. So is it true in all models? But and then in Hilbert's case, it was, I guess, more proof theoretically stated. But but this is equivalent, and that was the original gangster of decidability problems. And famously, it was shown undecidable by Church and Turing. I mean, they had to define what it means to be decidable in order to prove that it's undecidable, but they did that, and then they showed that it is indeed not decidable. So it's a foundational, the original undecidable problem. Okay. So if you want to avoid this undecidability, then there are two ways to go. One is to restrict the models, and one is to restrict the logic. Now, I will not say anything about restricting the logic in my talk. I'll just mention some examples. Are like one example is that if you only allow two variables in your formulas, well, at first it seems that you can't do anything, but in fact you can do some things, and this has been quite an intensively studied field in the last few decades. And there's techniques to solve that, which unfortunately do not involve automata. But they involve, say, linear, but integral linear inequalities frequently as a tool. And then there's lots of other fragments that people have introduced. But this is something that I don't want to talk about now. What I do want to talk about is restricting the models. So in the original problem, you care about any model. If you say just for finite models, it is also undecidable, so that doesn't help you. But as we will see in the following few slides, if you just care about models which are like words or trees, then you can get something from automata.
Mikolaj, we don't see the bottom of the slide now. Axis 2 at the bottom, we don't quite see. Do you want us to see? How much do you want us to see? How much do you see on your screen?
Well, there's an arrow which points downward. Is it better now?
Okay, now we see the whole axis 2, but just the text. Is there there's something smaller that I cannot read at the very bottom? Am I supposed to read it?
Do you see a downward pointing arrow with its arrowhead?
No.
No. Okay. That's what can I do? Is it better now?
No, now it chops. Okay, make it smaller. Let me see.
You know what? I'll try something else. I'll try to do an entire screen. Okay. Okay. Let me check if that will help.
Somebody said you should try to do Alt F5.
Nah, that's. Do you see now?
Okay. At the bottom there is some color. Am I supposed to see? I see pink.
Color is good. The color is a progress bar. Is that? Do you see a progress bar?
Like yeah. Now I see the progress bar. Yeah. Okay.
Good. And is there? Okay. Are you sure?
Now I see the progress bar. Okay.
But do you see something except for the progress bar, like the slides, for example?
Yes, I see the slide now. Now this is okay. Yeah, I think we are better now.
Thank you, Moshe. I appreciate that, because otherwise there would be nobody who would be telling me that you can't see my slides, and I would be like, this reminds me of a prank that some colleagues of mine did. So they were cleaning toilets as a summer job, and one of them liked to tell a lot of stories. So he went into the toilet, to use it actually, and then he started telling a story, and they encouraged him to tell his longest possible story, and then they left the toilet. So he was there telling this story alone, and then people would be coming into the toilet, and they would find this guy speaking from a toilet, and I was afraid that I would be like that person. So thanks for stopping me, Moshe. So where was I? Restrict the models.
Yes, restrict the models. Yes.
One axis is going to be words and trees. And then from that, I will say that you can push this further. And if you I'd like to mention tree width, which is an important option. And that's going, and as it will turn out, this is, at least if your logic is MSO, this is not only something you can do, but it is the only thing that you can do, which is nice, because then you can understand exactly for which models the problem is decided. So this gives you a clean theory. So let me begin with words and trees. So this automata method that I mentioned with Büchier, Elgot, and Trachtenbrot, where the theorem can be stated, I stated it in terms of natural numbers, but you can state it as follows. This is the way it's more usually stated, is that if you have a finite word over some alphabet, then you can view it as a logical structure where the underlying set is the positions in the word, and then you have one binary relation for order, and you have one unary relation for every letter of the alphabet, which is true in positions with that label. And then if you have a formula of MSO, which uses these predicates, then it's true in some words and it's not true in other words, and therefore you can think of it as defining a property of words, as long as you just evaluate it on structures which come from words. So for example, if you take the formula which says for every x there exists a y which is bigger and has label a, as long as you're talking about finite words, this formula describes, and your alphabet is AB, you're describing the regular language of words which end with A. So this is a regular language, and it's no coincidence because these are the same things. So regular languages are exactly the same thing as finite automata. And well, if you want to go from MSO to regular languages, you observe, well, this we already did this proof, in fact, that the finite automata, they have all of the closure properties necessary to deal with formulas. And if you want to go in the other way, it's very simple. You just formalize in logic the fact that an automaton accepts a word, and it's not so hard to do. So these are equivalent formalism, and this is, I think, how people view the Büchi-Elgot-Trachtenbrot theorem nowadays. I'd like to this is how you can view it, that you can frame it in terms of satisfiability, that given an MSO sentence, you can decide if it's true in at least one word, and the reason why that's true is that you can compile the formula into an automaton and check if that automaton is non-empty.
Sorry to interrupt you again. So now we have chopping on left and right and the bottom as well.
It's very bizarre. Well, thanks for telling this, but it's there's nothing happening on my side, and yet it's Okay, I'll do something. Maybe I'll do a different thing then.
Mikolaj, are you sharing your whole application or just the desktop?
I'm just sharing the desktop.
Okay.
Let me, maybe I'll do something. I'll not use my extra screen, and I'll do this something like. Can you see my slides again?
Yes, now it looks perfect now.
Okay, for a moment, but then I will be glancing sideways at you. Okay, well, too bad. And one thing that I want to mention here, which is expanded a little bit in my slides, is that there's a third approach, popular especially in baguette-eating countries, which is to use monoids instead of automata. And this is, I'll try to argue in my slides, it's quite a powerful approach. And for example, because monoids, they have a better structural and mathematical theory than automata. So for an automaton, I mean, what kind of decomposition results do you have in automata? What can you do in automaton? I don't know. Strongly connected components, number of transitions. That's basically what you can do with an automaton. So it's not very, very exciting. But monoids, they have a very nice theory where you can use the word group and other things, and this is quite a useful theory. So just want to encourage you to find out about monoids if you, yeah, I just wanted you to encourage you to find out about monoids. Anyway, the theorem about regular languages equal to MSO, it is true for many other things. So for example, for infinite words, because there are automata for infinite words, it is true for finite trees and also infinite trees. And because there are automata for all of these objects, and the automata are designed in such a way that they have the MSO closure properties. Now, I'd like to, from all of these things, I'd like to mention the one which is technically simplest, which is finite trees, because this will appear later on. So what is an automaton for a finite tree? So here's the picture. So you have a finite tree where you have nodes which are labeled by the alphabet, and say it's finitely branching, and well, it's a finite tree, so it's finitely branching in particular. And the way you run an automaton on it is that, well, in a word you put states between letters, so you do the same thing for a tree. You put states between letters, but now it's branching, so there's there's states like that. And then, so your transitions just tell you, as usual in an automaton, what is locally permissible. So when are states consistent in the environment of a single tree node. So that's your notion of transitions. And this was worked out by Hatcher and Wright in 1968. And they turn out to be determinized and be closed under complement Boolean operations because of determinization. And because of non-determinism, they're also closed under projection. So they're equivalent to MSO. This is technically rather simple. When you go to infinite trees, as in Rabin's theorem, it becomes enormously more complicated. But I don't want to talk about Rabin's theorem. But already the finite tree automata turn out to be a very interesting departure point, as I will explain in a moment. So that's word and trees, but it does sound a little bit ad hoc. Okay, so we have some method which allows us to treat some very special cases of models. So models which describe words and trees in some kind of way that's constructed to be compatible with automata. But as I will try to explain to you in a moment, it turns out that it is not so ad hoc at all. So this is connected to tree width. So let's say that I move beyond the words and I go to graphs. And graphs can actually be thought of as representing arbitrary structures, and this is provably so in this context. So let's think about say undirected and finite graphs. And then again, you can model a graph as a logical structure. There's several ways to do it. The one that I will use here is that the underlying set is the vertices and the edges. And you have one binary relation which tells you this vertex is incident or adjacent to that edge. There's other ways to do it. So for example, you could say that the underlying set is vertices only, and there's a binary relation for edges. If your logic is first order logic, it doesn't matter. If your logic is MSO, there's a difference, but I will focus on the incident model, and I'll explain the red thing later on. Okay, and this way you can express properties of graphs. So what can you say? You can say, for example, that the graph is connected in MSO, because when is a graph disconnected? A graph is disconnected if you can find two disjoint sets of vertices which are closed under taking edges. So you can express being disconnected, which you could not do in first order logic. Okay, and if you consider graphs, you can study the satisfiability problem, both for MSO and first order logic, but in both cases it is undecidable. And it is, well, roughly for the same reasons as the Entscheidungs problem, because you can encode arbitrary structures inside graphs. So this is an undecidable problem, but there's a reason for it. So if you look at the reason why first order logic is undecidable on graphs, or MSO is undecidable on graphs, the reason is that you can have graphs which look like this. So if you have a graph that looks like this, and say you have MSO quantification, then you can color it with the computation of a Turing machine. The rows are the configurations, and then you can encode the halting problem. And if it's first order logic, then okay, maybe you need to have some colors somehow in your graph, but the graphs that are important are grid-like. Okay, but what about graphs that are not grid-like? So here's a picture of a graph that doesn't look like a grid, and it's supposed to look a little bit like a tree if your eyesight is not good. Okay, and it turns out that graphs which are similar to trees, well, they're similar to trees, so things are good. So let me quantify this similarity, and this is a notion which is called tree width, and I will describe it using again a French way, inspired by Courcell's terminology, which is so using something as an algebraic structure. We're using something called graphs with ports. I think Courcell would call it graphs with sources. So the idea is this: you're dealing with objects which are, it's a graph, and there's some distinguished vertices which are colored here in red, and I call them ports. Okay. And then we can put them together in several ways, that I will describe in a moment. And then I will say that a graph is similar to a tree if it can be obtained from graphs with a small number of ports, using these operations. So the definition is that a graph has a tree width k, it's a number, if it can be constructed using graphs with ports that have at most k plus 1 ports, and using the following operations. So the first operation is a constant. So you can start with any graph with ports as long as all of your vertices are ports. So if k plus 1 is your upper bound on the number of ports, then you can create a graph with at most k plus 1 vertices because they all have to be read. The second operation is you input a graph and you indicate one of the ports and it stops being a port. Because, well, you want to allocate a new port. That's the general idea. Okay. And then the output is the graph with that port no longer being a port. And then the last operation is a fuse operation, where you have two graphs with ports, and you have a bijection between some of the ports, and then you just join them along that bijection. So there's, well, it's a bit underspecified here. So, yeah, but these are details I don't want to go into. So that's the operations you have. And if you manage to create a graph using these operations and keeping a small number of ports, then that means you have a small tree width. So let's see an example. So let me generate a cycle, a cycle of length 8 using at most 3 ports, and therefore it has tree width 2. This k plus 1 is just, it's a nuisance. It's defined so that trees have tree width 1. So how do you create a cycle? Let's begin with this little piece of a cycle. Everything is a port, so we're allowed to do that because there's 3 ports. Then we forget one of them. Then on the side, we could generate a new piece of a cycle, and then we merge them together using this fuse operation. And so we have a bit of a longer cycle now. And then we forget, so the important part of the cycle is the endpoints. And then on the side, we like attach to it another piece of a cycle. And then we prolonged it, we forget again. So we managed to create a longer path. And in fact, we could go on so forever. But I want to accelerate a little bit. So I do a symmetric film from the bottom. And then I fuse them and I get my 8th cycle. And then I forget all of my vertices. So you can see now why it's called tree width, because the reason why something can be generated is a tree. It's a tree of operations because it's an algebra. So it's that's the tree. Okay. And in fact, this works for, it doesn't matter what's the length of the cycle. Okay. So that's tree width. And then it turns out that tree width is exactly what you can do if you want MSO to be decidable. So let me state this. So this is something that was, well, this study of MSO on graphs was initiated by Kursel. And he showed, well, that the following problem is decidable. You are given an MSO sentence and a bound on the tree width, and you want to know if the sentence is true in some finite graph of tree width at most k. It's also true for infinite, well, countably infinite graphs, but let's say finite graphs, it's just simpler to see here. And the algorithm is very simple. You say that, well, you want to know if a MSO sentence is true in some graph of tree width k. Then, in fact, you can pull back the sentence so that instead of working on the graph, it works on the tree decomposition. I don't want to go into the details. I discussed this in my slides, my bigger set of slides. But this the result is that I get a new formula which is equisatisfiable, so equivalently satisfiable, but it works now on trees, which are these MSO tree decompositions, and then you convert that into a tree automaton, and then you check the automaton for emptiness. So this it's conceptually super simple. But what is beautiful is that this is the only thing you can do. So there's this deep grid theorem of Robertson and Seymour, which says that if a graph has large tree width, then it contains a large grid as a minor. I don't want to go into details what a minor means, but it's like a little bit similar to a subgraph, but a little bit more complicated. But it's similar to a subgraph. And then the definition of tree width is such that it can be understood by MSO. So the MSO can isolate a minor from a graph and then use that minor to describe a computation of a Turing machine. And it follows that for unbounded tree width, you're going to be undecidable. So if you have a class of graphs which has unbounded trees, then satisfiable is undecidable. So we now understand exactly what makes MSO's dissatisfiability decidable. It is tree width. Bounded tree width good, unbounded tree width bad. So that's, I think, pretty remarkable. There are variants of this result as maybe I should come back here. I mentioned here that there's this alternative choice where you have, there's the vertices only and an edge relation. And then there's a similar story, but which is connected to a measure of graph complexity called click width. But you have a very similar story. On the other hand, to be honest, I'm not sure how this works out. I don't think there's a good theory like this for first order logic, which would say exactly what is it that makes first order satisfiability as a structural graph property decidable. Okay, so that concludes the second part of my lecture.
Mikolaj, maybe it will be a good time to take a 5-minute break. This is
That's what I was, yeah, great.
2 hours, just a very long stretch. People can stretch their legs, run to the bathroom. So can you. Why don't we get back in about 5 minutes from now?
Sure.
If you have already taken your break, do you mind if I ask a question?
Forbid, no. I want to sit here, not moving. Go ahead, please.
So, if I were more interested on the automata side, and basically, what are the classes of graphs that are regular in that sense?
Mm-hmm.
Would the tree width kind of help describe such things as well through the link to MSO?
Yes, thank you. That sounds like a planted question because it's my favorite research topic.
Okay, great.
I like it because of several reasons. One of them is because it's monoids win with automata on this topic. Because there is not really a good notion of automata for graphs. It's a little bit ad hoc. but there is a notion of a monoid for graphs or a semigroup for graphs. It works well, but it works especially well for graphs of bounded tree width. And it turns out that, so there's a notion of regular language of graphs defined in terms of some kind of monoids. And so for unbounded tree width, they don't behave well. So they're undecidable, and there's other pathologies. But for bounded tree width, they correspond exactly to MSO logic. And this is a non-trivial result for unexpected reasons, because what used to be the hard part, so from logic to automata, so in this case, logic to semigroups, is easy. But the hard part is from well, semigroups to logic. And but this is true. So this is a relatively new result from like 4 years ago.
Would you mind afterwards sharing the reference for this on one of the Discord channels?
Sure, sure. Thanks. That's really. I mean, I can tell you what is the reason why it's difficult is that if you have a tree, then there's one way to parse it, bottom up, say. If you have a graph, it's not clear.
Mm-hmm.
But it turns out that there is an MSO definable way of parsing a graph, but that requires some extra results.
So if by magic I had a set of graphs that somehow have a distinguished node, like a root of a tree, then would it make it easier or not? Would not make a difference.
It wouldn't make it easier because you want to do recursion.
Mm-hmm.
So, I mean, the root, fine, but then what is the next node? You want to like run a program on it, which recursively decomposes. So it starts like maybe root of the tree decomposition, and then it branches out to the two children of that root. And then that's not clear how to run such how to describe such a recursive algorithm using monadic second order logic. But it turns out that it is possible. So in fact, there are many nice examples of actually the usually easy direction. So from say let's automata or semigroups to logic is the hard direction actually in many cases.
Mikolaj?
Yes, Anka.
Hi, Anka. So I just have a follow-up question. So if you have a way to parse the graph, wouldn't this offer the possibility to have an automaton?
Once you have parsed the graph, you get an automaton, but the way to obtain the parsing it's not at all clear how to write it as an automaton. So you would need to have a rather non-Catholic way of understanding. I don't know what kind of automaton. The usual ideas of automata would not work to parse the tree, to obtain the parse.
Or at least for a subclass of graphs that you get some kind of automaton from this parsing.
Maybe that could be done, but I'm not. This is so. The only thing that I can say with any confidence is that, well, if you what is an automaton? Yeah. Well, one way of saying an automaton, this is in the spirit of Büchi, which is that an automaton is an MSO formula of special shape. And if you use that notion of automaton, then I think you can prove that on graphs of bounded tree width, MSO collapses to something like 2 quantifier alternations, something like that, 2 or 3.
Mm-hmm.
But it's not 1, I think.
Yeah. Okay, thanks.
You're welcome.
So what's the special form of the MSO formula for words? What's
Well, if you formalize if you start with an arbitrary MSO sentence on words, you convert it on automaton and you convert it back again to MSO.
Mm-hmm.
You get a formula which says something like this: there exists a labeling of the word's position with state of the automaton, such that for every 2 consecutive positions, blah blah blah.
Mm-hmm. Okay.
So this is a formula of the shape. You have existential set quantifiers, and inside you have a very simple formula of first order logic, which in fact uses, I think, 2 variables or something.
Okay, thank you.
I guess we can wait for Moshe too. Hello.
I think we can restart, Mikolaj.
Okay, thanks. And I'd really, I'd like to encourage you to interrupt me also, yeah, all the time. So the last part, which will be a little bit more modern, is going to be about the model checking problem. The idea is this: I have a fixa formula, and then my input is, say, a finite graph. And I wonder, what can I say about the complexity of this decision problem? So it is useful because many classical problems that you have in algorithms can be described using first order logic. So if we start with, let's say this one. I contain a clique of size k. So this is a formula which depends on the k. So for every k, there's a different formula, but that's kind of okay. You just write out that there's a clique of size k. Another one, you can say vertex cover. Now, I hope I didn't make, well, always when I write a formula, there's a mistake in it. So I hope I wrote it correctly. There exist k vertices such that every vertex that's not among every edge has one endpoint in this covering set. And so consider this hypothetical question. Maybe for every first order sentence, there's a linear time algorithm, which the constant in the linear time depends on phi, but it recognizes graphs where phi is true. This is not unlikely to be true, or I think it's just not true. But if that would be the case, just I'd like to point out that the naive algorithm is polynomial, but the degree of the polynomial depends on phi. Yes, so you could just write an algorithm which replaces every quantifier by a for loop. It's the number of nested loops is the number of nested quantifiers. So that's it's a polynomial algorithm for every fixed formula, but well, it's not linear. Yes. So sometimes it can be done in linear time. So for example, vertex cover of size k, you can do it in linear time. So there is an algorithm which checks if there's a vertex cover of size k in the following time. So it is linear in the graph size, and then there is a coefficient which is exponential in the size of the vertex cover. So for every fixed k, it's linear time. So that's consistent with the hypothesis. But here's this clique of size k is inconsistent with the hypothesis because there's a conjecture in a field called parameterized complexity, which says that you cannot do a the clique problem with an algorithm which is not even linear, but even you allow it to be polynomial, but with a fixed polynomial. So the degree of the polynomial is supposed to be fixed, even if you allow yourself to be exponential or whatever in k. So you cannot do it in quadratic time. You cannot do it in cubic time. The degree of the polynomial needs to depend on k. So that's the usefulness of well, that's okay. Well, let me maybe continue. Those were things that you could formalize in first order logic. In monadic second order logic, of course, you can formalize much more. So say NP complete problems such as free colorability. Just say there exist 3 sets of vertices. Well, you just write out the definition of free colorability. The existence of a Hamiltonian cycle, you just write it out. It's useful here if you get to quantify over sets of edges, and in fact, it cannot be done if you can only quantify over sets of vertices. So there's, many algorithmic problems can be formalized just by writing out their definition in logic such as first order logic and MSO. And therefore, if you have a generic algorithm which works for every formula of, say, first order or MSO, then that is going to be a useful generic algorithm because it will work for any algorithmic problem that can be formalized in these logics. So here's 2 generic algorithms. I begin with a very simple one, which is by Cese, which says that for bounded degrees, and so here we fix the formula, but it's not going to work for all graphs. It's going to work for graphs of bounded degree. So more precisely, if you fix a sentence of first order logic and you fix the degree, then you can solve in linear time the question if a graph satisfies phi. Moshe, you look suspicious.
No, I'm okay. Yep.
So I'll give you a rough sketch of a proof. It's not so hard for this theorem, and it follows that any problem that you can formalize in first order logic, such as vertex cover or clique of size k or whatever, that problem is going to be linear time on graphs of degree d, of fixed degree. It's linear time, but the coefficient of the algorithm will depend on d and k. Another example is for MSO, and it is a famous Courcelles theorem, which says that you can do the similar thing for MSO and bounded tree width. So it says that for every fixed sentence of MSO and every fixed bound on the tree width, you can evaluate in linear time sentences of MSO on trees of that tree width. So a corollary of this theorem is that any problem you can formalize in MSO, such as free colorability or vertex cover or stuff like that, you're going to be able to do it in linear time on graphs of bounded tree width. So, for example, you can check Hamiltonian path on graphs of bounded tree width in linear time in terms of the input graph, as long as the tree width is bounded. So let me begin maybe with a brief overview of how you deal with Courcelles' theorem, and then I will move to the first order logic part. Such theorems are called algorithmic meta-theorems. They're meta in the sense that they solve not just one graph property, such as clique, k-clique, or vertex cover, or three colorability, but they immediately give you an algorithm for any kind of graph property that you could state in the accompanying logics. So for bounded degree, it's going to be first order logic, and for bounded tree width, it's going to be not just first order logic, but even bounded tree width. So let's have a look at the Courcelles theorem. I won't say too much about it, but it follows the lines that you would expect. So there's 2 ingredients, one of these which is of a non-logical character, and it is Bodlander's algorithm for computing 3D compositions. So it says that for every fixed tree width bound k, you can compute the 3D composition in linear time. The coefficients are exponential in k. It says, I think it's so this is it's a rather hard algorithm. There is a much simpler algorithm, which is in Robertson and Seymour's original papers, which is, I think, cubic, and it doesn't give you an optimal width 3D composition, but it would be good enough to get Courcell's theorem with cubic instead of linear. But you can do it in linear time, as shown by Bodlander. So it's a rather complicated construction. And then the second lemma says that once you do, so you first compute the 3D composition in linear time. The coefficient is exponential in k, but that's fine because the k is fixed. And then the second lemma says that once you're given the 3D composition of the sentence, you can evaluate it in linear time. And the reason is because you compile the MSO sentence into an automaton and run it on the 3D composition. That's consistent with what I described before for the satisfiability problem. And then there are similar results for if you replace tree width by a different graph measure called click width and rank width, but I don't want to go into those. Okay, so this is the automata method. So the automata method says that if your graphs look like trees, then you can run 3 automata on them, and then that's what it says. But what I'd like to finish my tutorial with today is a discussion which goes in a different direction, which is not related to automata, and which is the story about theorems such as Caesar's theorem and similar ones for first-order logic. So this is what I wanted to finish with today. A few words about that. When I was using MSO, the main ingredient was the automata method, which says that you can compile MSO formulas into automata, or if you think of it more like a logician, it's something called compositionality of MSO. So compositionality of MSO says that if you have a graph and it's decomposed into two parts, a left part and a right part, and then they overlap in a very small way, then in order to evaluate MSO on the entire graph, all you need to know is what happens on the left part and what happens on the right part independently, and then maybe some information about how they overlap. That is something called compositionality of MSO. It can be phrased in terms of a suitable game, or it's a lemma about MSO, which is what makes all of the automata methods work. When we're dealing with first-order logic and theorems such as the Caesar theorem, it is a different aspect of logic that we care about. For first-order logic, it is something called locality. And in the theorems that I will cite, it is Geifmann's locality, which is the following result, which it says that every sentence of first-order logic on graphs is equivalent to a Boolean combination of very special sentences, which look like this, are called basic local sentences. And they say that there exist k vertices such that, well, they're far away from each other. So, well, there's some parameter k, which is how many vertices, and there's some parameter r, which says how far away they're supposed to be from each other. And then in each one of them, you evaluate a formula which is local. And local here means that it's not a random formula of first-order logic, this phi, but it is a formula which has the semantic, but this can also be described syntactically, property that it only depends on a bounded degree radius around x. So a local formula is one that depends only on the vertices which are close to x. So that's why it's called locality. So the formulas phi of x, which are used here, they don't look far away into the graph. They look only in a close neighborhood of x. And Geifmann's theorem says that this is the only thing you can do in first-order logic. So
sorry, should it be here like phi of xi or something like that? Or
correct. Yes. It should be phi of xi. Thanks. That's yeah. I hope that fixes it. Yeah, thanks. Thanks for pointing that out. So there's also, you can discuss the complexity of it, and there's work on that it's, well, not so good with complexity. As always, when translating formulas of logic into a normal form, it's really bad. You do get lots of nested exponentials. But if you think that the formula is fixed, it's fine. Okay. So this
sorry, once again, there's the same formula for each xi, or is it different?
It is the same formula for each xi. So let's use this locality theorem to prove Cez's theorem. I mean, I give you a proof sketch in my slides. I give you a more fuller proof. So how do you do it? So suppose I want to evaluate, want to give you a linear time algorithm for evaluating first order formulas. And so how do I evaluate a basic local sentence? Okay. Well, my degree is fixed, the sentence is fixed, and I want to evaluate it in linear time. So for bounded degree graphs, it's kind of easy, because to evaluate local sentences, you don't need to look very far away, because the R neighborhood around the vertex has constant size. So you can just evaluate phi in constant time by just brute force. Okay. That explains the main idea. That doesn't explain the entire algorithm, because now you want to say if there exist like these vertices which are far away from each other, which have this property that you can evaluate in constant time. But this you can work out. It's not entirely trivial, but it's a slightly smart variant on a greedy algorithm. You have to be a little bit clever there, and I'll try to explain it in my slides. Okay. So for bounded degree graphs, you can evaluate using locality, because, well, the localities are constant size. You can evaluate every first order sentence in linear time. Okay? And then it turns out that there are far-reaching generalizations of this result. And I'd like to survey two such generalizations, which are relatively recent results. So one is about nowhere dense classes of graphs, and the other one is about a notion of graph complexity, which is called twin width, which is like kind of fresh. So it's like last year or the year before that. So let me begin with nowhere dense. So nowhere density is not a property of a graph, it is a property of a class of graphs. So here are examples of classes of graphs which will have this property of being nowhere dense. Graphs of degree at most 5 or 7. And any bounded degree graph class will be nowhere dense. Graphs of tree width at most 5 or 7. This is also going to be nowhere dense. So for every fixed, if you bound the tree width, then you're going to be nowhere dense. Another example is planar graphs. These are also going to be nowhere dense, the class of all planar graphs. Graphs that avoid the 5 clique as a minor. And in fact, any excluded minor class, which covers well, the bounded tree width and planar graphs examples. This is going to be nowhere dense. And then, so there's a notion of nowhere dense classes, which I will describe to you in a moment. I'll just give you the definition, nothing more. And then the theorem is going to be that you can do it, you can do first order evaluation in linear time for every nowhere dense graph class. So not only for graphs of bounded degree, as in Cez's theorem, not only for graphs of tree width at most 5, but for planar graphs and so on. And there is and this you will be able to do it for every class of graphs which is nowhere dense. So what I'm going to do is I'm just going to give you the definition. So when is a class of graphs nowhere dense? As I say, it's a property of a class of graphs, not of a single graph. So it's defined using minors, and now I will define this a little bit more precisely. So suppose you have a fixed radius, and you have 2 graphs. And what I'm going to say is, what does it mean for H to be the red graph, to be a minor of the black graph, but with this bound on the radius R? So I say that H is an R minor of G. If you can, well, sort of embed H into G in the minor way, except that you need to use short paths. So what does that mean? That you can associate to every vertex of the red graph a set of vertices in the black graph. This is as usual, as you usually do in minors. Okay. And then you have the following properties. First of all, this is the R that intervenes. These parts, the red blobs in the graph G, which are supposed to simulate vertices of the graph H, they have to be connected, but not just connected, but they need to have small, well, radius. So there has to be, in each one you can find a vertex such that all others are reachable via at most R edges. Okay. So if you talk about the usual graph miner, you don't have no limits on the radius. Here, you have these blobs have to be small. I mean, small in terms of radius. If the graph has high degree, then they will be large in terms of numbers of vertices. And then the second property, well, this is what you expect, is that you can recover all of the edges in the graph H. So if two vertices are connected in H by an edge, then the corresponding blobs in the graph G will be connected by an edge. So there will be an edge from one blob to the other. So if you lift the restriction on R, so let's say you say R is equal to infinity, then you get the usual graph minor relation. But now we care about a more fine-grained approach to it, where we do bound this R. So we want this minor to be witnessed in a small local way. And local, it's no coincidence because it's going to be useful for locality. Then the definition now is this: a class of graphs is nowhere dense if for every radius R, you look at all of the R minors of the class, and you're not supposed to get all graphs.
R minus of C means R minus of some graph in C.
Yes, correct. Okay. So maybe I think it's a good thing to just spend some time with this. So maybe the contrapositive, the negation, I think. What does it mean to be not nowhere dense? It means that there is some radius such that within that radius you will find all graphs. Okay, so you have all graphs as minors, but not just as minors, but as minors with the vertices being small blobs, bounded radius blobs. Okay, so this is a definition, but what is wonderful about this notion is that there's like 8 other definitions which are equivalent to it. So it seems to be a super robust notion of graph classes. Okay, so maybe let's have some examples. So the class of bounded degree graphs. Then this is nowhere dense, because if you fix the radius of your blobs, then they will have constant out degree because it's a bounded degree graph. So you cannot go too far away. So you will also, for every fixed radius R, you will get also a bounded degree graph as an R minor. Well, with the bound on the degree being exponential, but still being constant. So you when you fix the radius R and you look at the R minors of that kind, you will also have a class of graphs of bounded degree. So you will not get all graphs. So every class of graphs which has bounded degree is nowhere dense. Example 2. If you have bounded tree width, then you are also nowhere dense. And this is because even if you take R equals infinity, you're not going to get all graphs as minors because it's an excluded minor graph class. Because, well, for tree width, for example, you cannot find the k+1 clique as an R minor for any R. This is you can show it. So here it's even a stronger property, which shows that every excluded minor class is nowhere dense. But for example, a bounded degree is not an excluded minor class. Okay, so this is a notion of density of a class of graphs. And now the theorem says that for such graph classes, first order model checking, well, it's not really linear, but it's almost linear. So it's a theorem of Grohe, Kreutzer, and Sieberts, which says that for every nowhere dense graph class, there is an almost linear, well, you can find an algorithm which is, well, not linear, but n to the power of 1.1, n to the power of 1.001. You can evaluate first order formulas on that graph class in n to the power, and the power can be arbitrarily close to 1, as you wish. So it's almost linear model checking for every nowhere dense graph class. So this generalizes Cesar's theorem. It generalizes the variant of Courcelles' theorem for first order logic, and it generalizes a lot of other theorems. And in fact, it generalizes all theorems in the following sense: that if you care about, well, about graph classes that are closed under subgraphs, so your property of graphs is closed under eliminating vertices and eliminating edges, which is the case for all of the examples that I gave, then nowhere dense is the exact border between when you can do a first order model checking and when you cannot, in terms of, say, fixed parameter tractability. So if you take a class which is not nowhere dense, and it is closed undertaking subgraphs, then model checking on this class is as hard as model checking on general graphs. So you inherit all of the trouble from that. And this is rather, I mean, it's just an unfolding of the definition, because if you are not nowhere dense, that means there's some number r, say r equals 12, such that you can get every possible graph as a 12 minor. And then by closure under subgraphs, it means that you get, well, roughly speaking, all graphs with edges simulated by paths of length 24, I think. There's some small technical issues, but it's rather straightforward to see. So here there's again this nice dichotomy. So we know exactly what it takes for a class of graphs to have linear, well, fixed parameter tractable, in this case almost linear model checking. So if it is almost if it is nowhere dense, then it is close to linear, and if it is not nowhere dense, then it cannot be done in quadratic time, it cannot be done in cubic time, and so on. Okay, subject to some conjectures about fixed parameter tractability. So that is one line of work, and I'd like to finish my talk with a final rather recent development, which is something called twin width. What is it? Well, here are some other examples of graph classes where first order model checking is in linear time. So you take, instead of planar graphs, you take complements of planar graphs. It's a very stupid trick, yeah? So instead of saying edge, you say non-edge, and the opposite. So of course, it's the same problem as evaluating first order logic on planar graphs, but it is not a nowhere dense class of graphs. You can, because, well, it has lots of edges, okay? That's one of the characterizations of nowhere density, is that you do not have a quadratic number of edges. Okay, it's a stupid trick, but it's already a class that's not nowhere dense, and it's easy. Or, you know, a complement of any other nowhere dense class, that's also going to be easy, because complement, first order logic can deal with complement. Another example which doesn't fall into the stupid complement category, but almost does, is graphs of clique width at most 5. So clique width is a notion of graph complexity similar to tree width, but different. It's meant to cover cliques and graphs similar to those. I will not go into the details, but this is, you can also do first order. In fact, MSO model checking, I think in linear time, definitely in quadratic time or something. Okay? For fixed parameter tractable. So these are classes which are not nowhere dense, and importantly, they're not closed under subgraphs. So they're not covered by the dichotomy theorem that I mentioned before. So it would be nice to have something which covers these dense classes. Dense meaning lots of edges in this case. And well, this is not the theorem that I will mention now. It doesn't cover all dense classes or classify them in some full way, but I think it's an exciting development which generalizes many results about dense classes, which is a notion of graph complexity called twin width. So all that I'm going to do is I'm going to define twin width, and this will be roughly the end of my talk today. So what is this twin width? So imagine you have a graph and you partition the vertices into some groups. In this case, there's 3 groups ABC, okay? So I say that 2 blocks, so groups in the partition, are consistent if they're connected in the same way. So blocks A and B are consistent because for every vertex, no matter which vertex I choose in A and no matter which vertex I choose in B, there's always an edge. So I don't care what happens inside block A. I don't care what happens inside block B. I care about between A and B. Okay? So they're consistent in a yes way, and blocks B and C are consistent in a no way, in the sense that for every 2 vertices, there is a non-edge. Okay? And blocks A and C are not consistent because sometimes there is an edge and sometimes there's not an edge. Okay? Is this clear? So now, using this idea, I'm going to define twin width. And this is something by Bonnet, Kim, Thomas, and I don't know Watrijan, that I don't know how you from last year, so it's pretty recent, and it's the following definition. It says that a graph has twin width k if you can obtain it as follows. So you can have a sequence of partitions with the following properties. You begin with the trivial partition where every block has one vertex, and you finish with the partition which is trivial in the other way. Okay, so you you merge, you're going to merge partitions. Then when you go to the next partition, you just merge two blocks of the preceding partition. Okay, so at each step, you're going to merge two blocks. Okay, and then, well, the last, of course, the place where the entire definition is item C, which says that at every step of this process, and you look at one block in the partition Pi, then it is consistent with almost all of the blocks. So with at most k exceptions, it's consistent with every other block. In other words, if you think like in the ith step, you think about the graph where the vertices are the blocks and there's an edge for an inconsistency, then this inconsistency graph has a degree, out degree or in degree, with degree at most k. Okay, is it clear? That's the definition. Let's see some very simple examples. Let's say clique width. Well, clique for the moment. A clique, it has twin width 0 because you can decompose it without any inconsistencies whatsoever. So you, I should have, I should have started out with my singleton blocks. So I don't draw them. Okay, so initially everybody is in their own block. Okay. And then I merge the first two blocks. Okay. So what are my inconsistencies? There's no inconsistencies because, there's an edge everywhere. And then I merge the first three, well, I add the third vertex to this block. And then I keep on merging. And at every moment, I will have 0 inconsistencies. So it has a twin width 0. Okay. Another observation is that this is not, it doesn't care about edges. It doesn't make a difference between edges and non-edges. So if you complement it, the same decomposition works because it's instead of being yes consistent, it becomes no consistent, but it's still consistent. Okay? So this is a measure of complexity, which doesn't. It's like it's not positive in the sense that fewer edges is better. It doesn't care about complementing graphs. And in fact, you can show that bounded tree width implies bounded clique width implies bounded twin width. So these are measures of complexity. The middle one I didn't mention it, but I mentioned, but I didn't explain it. But bounded twin width generalizes these. So every class of every class of graph which has bounded tree width will also have bounded clique width, but you can convert a clique width decomposition into a twin width decomposition. No, I don't know. I don't remember. Maybe k grows exponentially or something, or maybe it doesn't. I don't remember. But it's definitely bounded implies bounded. So any algorithm that will work for bounded twin width is going to be stronger than an algorithm which works for bounded clique width. And in fact, there is such an algorithm, but for first order logic. So in the original paper, in the paper that defined twin width, they show that for every, if you fix the twin width and you take a fixed first order formula, then you can evaluate it in linear time on graphs of twin width at most k. There is a caveat here. So there is no Bodlander algorithm. So the algorithm, it requires not only the graph on input, but it requires this twin width decomposition. And then you can evaluate first order formulas in linear time. And so far, well, it's a new thing, but I believe there are no, I don't think there are fixed, there's no linear or cubic or whatever algorithm for computing a twin width decomposition for every fixed k. And so that's, I think, a nice new development, and there's some theory being built up about it. So if you want to look at it, I encourage you to have a look at it. And I think that's all I wanted to say in my talk. So there's this beautiful story, which is rather recent, about understanding for which graph classes first-order logic can be evaluated efficiently, like in linear time. And then there are these strong results which say, in these cases, you can evaluate it super efficiently in linear time, and in the remaining cases, it's impossible. Not linear, not quadratic, not anything. So these are, and there's quite a lot of deep theory involved there. And then there's also the classical story of, well, relatively classical, of MSO and Courcelles theorem. And there's also some developments in that. And I think that would be the end of my tutorial. So thank you for bearing with me for all of this time. And if you want to have a look, then you can, on my website, and I think on Simon's website, you can find links to extended versions of these slides. And thank you.
Thank you, Mikolaj. So I have one question. So in some sense, I would say the most, I don't know, famous or in practice kind of tractability result for this kind of question, of course, are the two results in temporal logic, right? The CTL model checking and LTL model checking are both linear in the size of the structure. Do they follow from anything that we have seen here? Does this follow from anything we've seen here? Because this is true for arbitrary graphs, right?
No, but I think there is an automaton perspective on it.
No, of course there is an automaton perspective.
No,
I know
that. There's one that maybe it might not be your perspective.
Okay, is there another one? Okay, tell us.
No, I don't know. I mean, I'm just trying to be controversial here.
No. I mean, the key thing is that the quantifier, in some sense, the quantifiers here, it's a second, you can think of them over arbitrary structures. This is both LTL, because we're asking about question about the graph. The R, it's a monadic logic here, in some sense. But the set quantifiers are special, and they are about paths. They're not about sets. They're about paths. I think that might be special here, which means there is a maybe the key thing is to look at yet another logic, which is in between first order and monadic and full monadic. And I think maybe Wolfgang Thomas have looked at it, called path logic, where the quantifier are over path.
Yes, so this is, so I tell you what is my perspective on it, which is that these are, and it is, well, it's not, these are, one way to look at temporal logics is that you have a multi-step process where you label your structures by the true values of more and more complicated formulas, of node formulas. This doesn't really work for LTL or, well, for CTL star, but it does work for LTL and on strings, and it does work for CTL on graphs. And I think this perspective of adding more and more labels is connected to a very classical topic in automata theory and algebra, which is Cronrode's decompositions. So I think this would be for me the perspective that is useful here. And this is a line of work that you concentrate on node formulas, which have just one free variable x, and then you keep on adding labels to your structure, which say more and more about it. This is something that was developed by, I think it's a very beautiful, a very simple idea by Luc Ségouffin, which is these unary negation fragments, for example. So so this is another perspective on such temporal logics, which is connected with these Cronrode's decompositions, which I think are a beautiful topic and a bit underutilized in the literature, in my opinion.
Any other questions from the audience? Again, remember, there is a more extensive set of slides and recording available, should be, I think, to the Institute website. Well, if there are no other questions, then let's thank Mikolaj again for a wonderful tutorial. And People from the West Coast can start the day, and people from Europe can finish the day. And we'll see you all tomorrow here continuing. Take care. Bye-bye. Thank you, Mikolaj.
Thank you.
Hi, Mikolaj.
Actually, may I ask a quick follow-up question?
Yeah, go ahead.
So this, the parts in your definition of twin width, which was related to having a sequence of partitions, is that sort of related to the same being able to parse the graph that you mentioned? As in, if I have partitionings at every level that satisfy your condition, but they're not connected through these moves together, then it would be strictly weaker than the definition that you gave, right?
Can you repeat the alternative?
So you kind of start from these singleton partitions and step by step go to this everything in one partition. So imagine the alternative in which I have these partitionings at every level. If we think about this kind of partitioning lattice, think about it, right? But your definition requires me to be able to connect the dots, right? I can all of these have to be related by these moves, merge moves together. Is this extra condition, as opposed to just the existence of a partition at every level, such that it satisfies your condition? Is it related to the same parsing of a graph, as in I have a strategy?
Well, of course it is. I mean, if you think about this lattice of partitions, then it is, yeah, what you want to have is a path through this, as you said yourself, a path through this lattice, which says that the consistencies are, yeah, you want to have that, and finding this path. Well, it's nobody knows how to do it, I think.
No, I'm more. So my first question is the existence on the existence of the path. So imagine a slightly weaker definition. At every level, as in at every level of this lattice, you do have a partition that satisfies the consistency at most k inconsistencies, but the ones from each level are not connected together by merge moves.
I mean, I'm not an expert on twin width, but my intuition would be that this is very different. That you can have complicated graphs such that on every level you can find a simple partition, but you cannot connect them by a path somehow. That would be my my impression about it. So you can, the fact that you have to do it in a consistent way, I think it should be different.
Right. I think my question was general, to kind of try to get an intuition why they have to be connected. What purpose does that serve exactly? But well, I know
the purpose that it serves is that, imagine that what you're going to have is a first order evaluation algorithm which computes some information about the ith partition. And then, well, since the I plus first partition is very similar, it doesn't need to do too much more work. It's like incrementally going to change it. So that's the idea. That's what you gain from it.
Okay, that makes sense. And one other quick question is the Geifman theorem, the phi, is that computable?
Yes. Well, yes.
So
okay, it sounds suspicious because first order is undecidable on graphs. But the Geifman theorem says that you can compute some phi, but probably the optimal ones are uncomputable. But some non-optimal ones are computable, yes?
So the theorem says that it exists, or it says that it can be computed?
It can be computed, yes.
Okay, yes.
So it's like many things about, most things about semantic properties of first order logic are undecidable on graphs. But this is more like a syntactic translation somehow. It's a bit more, it's more complicated, but in the spirit of converting a formula into a pre-next normal form. So there's an algorithm which does this. I mean, probably computing the shortest possible pre-next normal, well, not probably, but provably computing the shortest possible pre-next normal form is an undecidable problem, but some is decided.
But computing the phi is a simpler question than the actual model checking question, or no, it's equally hard? Well,
computing this, I think it's the algorithm is non-elementary. The size of the output formula is non-elementary, so it's worse than a tower of exponentials. It is a tower of exponentials or something. It's worse. I don't remember in terms of the size of the formula. So in that sense, it's very bad. But since you think of the formula as being fixed, then I think they're incomparable, these results, because one is non-elementary in the sense of a tower of exponential or worse. But on the other hand, since our perspective is that the formula is fixed, we don't care about that.
Thank you very much. Excellent talk.
Thank you. And I'll send you the
link to the paper. Yes, that would be, yes. Thank you very much.
Thank you.